Okay, good evening ladies and gents. Apologies for breaking up any conversations, but with no further ado, I'm going to introduce tonight's main speaker. This is Mike Crawford, and apologies if anybody knows me, I've got a memory like a sieve, so I will read it from this. Mike is the Strategy and Business Development Manager for Rolls-Royce SMR, utilising a wealth of experience in the nuclear industry to help meet the twin challenges of decarbonisation and energy security. Specialising in technology introduction programmes. Mike has worked across the breadth of the nuclear industry. Now with Rolls-Royce SMR, Mike is working with utilities, energy users and policymakers to develop new scalable models to deploy nuclear solutions in the industrial energy ecosystems of tomorrow, I would argue possibly today, driving down the system cost and the energy transition. So with no further ado, let's welcome our speaker, Mike Crawford.
Thanks, Scott, and yeah, pleasure to be here. Thanks for the invite. So, as Scott said, you know, SMRs particularly are in vogue at the minute, and there's a flurry of activity that's been building over the last sort of 5 years. That was the premise of the creation of this presentation. So I support in the Derby Centre IOP, as well as working for Rolls-Royce. When I made this presentation, I was trying to take my Rolls-Royce hat off. This was a sort of neutral, as you can be, presentation around the wider SMR landscape. But I guess I have some biases, so to take what I say with a pinch of salt. When we conceived this presentation, it was in two parts. So I am sort of the expert on SMRs of the future, because that's my day job, and the brilliant Oliver Lonsdale put together the first half, which is all about SMRs of the past. So I'll deliver them both today, and I'll do my best job of imitating what Oliver would have said in the first half. But I guess, fair warning, it's not my speciality, what happened sort of 70 years ago, so I'll do my best if there's questions, but I'm more an expert on the second half. So, this sort of fever pitch that we're at now for SMRs and nuclear deployment, it's not the first time there's been this enthusiasm for nuclear technology. So the first time was straight after the Second World War. We'd harnessed the power of the atom and all of the potential that there could be in that science had really just started to kick off. So there were lots of R&D activities, lots of money being spent into nuclear science, which was a relatively new science. There were some civil initiatives, so some of you may remember President Eisenhower of the US had a famous Atoms for Peace speech and initiative that was all around sort of the peaceful use of nuclear power. But by and large, in this period, the vast amount of R&D and the vast amount of sort of development activity was all in the military sphere. Some of that you may be familiar with because it was quite successful. That was the Naval Nuclear Program. So the Navy, for submarines and then eventually other things like aircraft carriers, they had a hugely successful development program that essentially bred the modern day nuclear industry. So most of the sort of plants we see around the world, in some way or other, are evolutions of what came through that program. So does anybody recognise the guy on the top? I mean, the name's on there, but does anyone know? Are people familiar with who that is? Because I think it marks you out. If anyone's worked in the nuclear industry, you're probably quite familiar. It's Hyman G. Rickover. So he was a US admiral that led the Naval Nuclear Propulsion Program, and he is famous for doing a really good job and being a great leader. And he set out 10 principles that may as well be called commandments that the nuclear industry today essentially still follows, and they became what is nuclear today. We call it nuclear safety culture, and it's about that. Doing it right, because this technology can't afford to go wrong. And so he was instrumental in sort of creating that culture at the very outset. And I guess no surprise that the programs he led were so successful. Some of the other programs, and at this point, it's a new field. R&D is going out in lots of different directions. There's all these different technologies, and this one might be good, this one might be good, this one might be good. If you put a pin in that for what's happening today, there's quite a lot of parallels. The program we'll look at, that's not the naval program, so today we'll look at the Army Nuclear Power Program. and they launched a series of reactors. So each one of those down on the right-hand side is a different reactor, all slightly different. So they used a few different technologies, a few different locations and use cases. But the reason, the drivers for them pursuing this, so you can see the goals here, and if you scan down them, they're not that different again from what we're doing today. So reduce dependence on fossil fuels, reduce the logistics burden, reliable, continuous power, infrequent refueling, reduce maintenance and get the cost down. The one thing that's different here, and I think sets the Army program apart from the Naval program running at the same time, was that transportable nature. So they had the objective of being able to put these, in war, behind enemy lines, or to power all those forward operating bases. And even this idea, everything is coming back around, and portable nuclear power is absolutely on the radar. The US military have a project called Project Pele, and they just earlier this year, in fact last month, kicked off a huge initiative to go and put that into production for portable nuclear power plants. So this is how the program developed over a period of about 20 years. So you can see on the bottom is the Army program. The top is the counterpoint of the Navy. So by the time this program was established, so here, 1954, we already had the first nuclear-powered submarine. So immediately it's behind. And as we go along, so the first prototype reactor was SM1. We'll talk a bit in detail about PM3A in Antarctica and MH1A in Panama. But by the time we're doing, sort of the more interesting stuff, compare that to what's going on in the Navy program. You've got 26 nuclear submarines, and you've also just commissioned your first nuclear aircraft carrier. So all throughout the history of this program, it was sort of competing against a more successful and more favoured big brother. And then, for a variety of reasons, lots of them political, it was shut down in 1977. That being said, lots of learning still came out of this, lots of technology development, and all of that, both the top and the bottom lines here, went into then what became huge rollouts of civil nuclear power across the US, but also across Europe, and following that, then other parts of the world. So, a couple of big successes that came out of the Army program was the variety of designs that they tested. So they did the first versions, the prototypes of some of these more novel technologies like gas-cooled reactors and liquid metal reactors. And they were starting to think about the different roles nuclear could play. So all of these reactors were the first examples of nuclear to electricity. But the Army were thinking about, well, how can I get the heat to power to warm my bases in Antarctica, as an example? And can I desalinate the water with this heat and with this electricity? And so they started to experiment with the different applications for nuclear power. And also, it bred a huge sort of workforce that again seeded that civil nuclear power takeoff in the US. It also started nuclear's storied sort of history with being closely knit with the political sphere. These days nuclear and politics go hand in hand. Part of that is because nuclear power plants are quite big and expensive and take a long time, and so you need entities like governments that can take levels of risk and have long planning horizons to a degree. But it got tangled. I think nuclear's been tangled a little bit too closely with politics, and we're hoping that with SMRs, by making these things more of a commoditized product, we can start to pare back some of that and get to take destiny into our own hands, which would be nice. So, the first reactor we'll talk about in a bit of detail is PM3A. So I think it was the third in that list of all the reactors. For some reason that's lost to me, certainly, it was nicknamed Nuki Poo. I'm not entirely sure why. I don't know if Oliver does. I'm not sure he said it when he delivered this the first time. But it was deployed in McMurdo Station in Antarctica. So a difficult deployment by any standards, let alone for a nuclear power plant. It was pretty small, so if we get chance and there's still enthusiasm in the room, later we can watch the video. But it's essentially like a cylinder, like a big gas transport cylinder, and so they shipped it in on essentially a shipping container on a ship, and took it out, set it up. They piled loads of earth around it for shielding, so to shield the inhabitants of the base from the radiation. They essentially piled a load of Antarctic earth around it. It operated for about 10 years, and at the end of that, it was taken down, one, because there was some issues with it, so they found cracks and leaks, so they had to shut it down. But when they took it away, they found that all the earth that they'd used for shielding was, surprise, surprise, radioactive, which I guess probably shouldn't have been a surprise to any of the nuclear physicists on the programme, but I think it was certainly not in the awareness of the people controlling the purse strings, who then had to have basically men go in and ship all of that earth to be responsible stewards for nuclear technology. They had to go and get that earth and ship it, and they ended up incorporating it into a US naval base, into the asphalt. And I assume, not looking into this in detail, but I assume there's principles like Fukushima wastewater release. If you distribute this thing out among 10 square miles of asphalt, it's not that radioactive. But yeah, that's the sort of stuff that happened in the 70s. But nonetheless, although the specific reactor stopped because it had cracks and leaks, it operated, giving power, heat, and in the middle of nowhere, Antarctica, for 10 years, which is something that only nuclear power can do. And so it starts to give you a flavour there for that, the energy density, the long life of nuclear power, and how that can play a part in energy systems. The next one, we'll watch a quick video first. It should work because we tested it earlier. I think half the room looks to be about under 20, so believe it or not, TV used to look like this. Is that working? Oh no. Used to sound like this as well. What amazes me is they had this technology for what you're about to see from a nuclear power plant.
When the forces of
Yeah,
nature,
this is what video looked like.
the anger of the sea, the fury of the wind, or the grinding cataclysm of an earthquake encounter man's works, disaster often ensues. But nature is not the only destructive force. Following disaster, man must restore, but his efforts are often hampered by the absence of that modern-day genie, electricity. Recovery from such disaster is highly dependent upon supply lines and availability of electrical power, long-term, reliable, self-sustained power. To meet the challenge of these requirements, the Corps of Engineers conceived the MH-1A floating nuclear power plant. This concept provides mobility by mounting a 10 million watt electrical power plant on a seagoing barge. A nuclear reactor heat source eliminates the need of a continuous supply of fossil fuels required for the non-nuclear power plant. This power plant, traveling the oceans and inland waterways of the world, can bring electrical power to any point accessible to ocean-going vessels of moderate draft. The basic concept was developed into a detailed specification by the Corps of Engineers at Fort Belvoir. Preparation of the specification was in itself a big job. The specification requirements highlights are these: conversion of a World War II Liberty ship to a manned, non-propelled barge for ocean service inspected and certified by the United States Coast Guard. 10,000 kW net electrical output. High availability. Refueling once a year. And a one-year supply of onboard repair parts. To give substance to the floating nuclear power plant concept, the Corps of Engineers selected the nuclear division of the Martin Marietta Corporation as prime contractor. The contract was let by the Corps of Engineers Philadelphia District Office. The prime contractor, in turn, selected the J.J. Henry Company.
Stop it there, but just go and watch the whole thing. So we're introducing another new concept here. You know, this is a floating nuclear power plant. These sort of concepts do come back around, and they're in the news quite a lot. There's a number of companies, some of which have raised huge amounts of money for floating nuclear power concepts, and we now have talk again of nuclear for propulsion. So the big shippers, people like Maersk, are really interested now in how, for long distance point-to-point shipping, you know, sort of China to America, how can they utilise nuclear power to power their big, you know, the giant cargo ships, rather than bunker fuel, which is the most polluting fuel we have. So this floating power plant, when it was conceived, the intent was that it was going to Vietnam. So it's going to support the war in Vietnam. By the time it got built, the war wasn't going so well for the US, and they'd had a lot of bad press about the use of various chemical agents. And so politically it was decided that sending nuclear power, and there was also a sort of anti-nuclear movement sort of gaining strength at the same time. It was considered political suicide to send a nuclear power plant over to Vietnam. Handily, in some ways, the Suez Canal was closed at the same time, so there was a big crisis in the Middle East, which led to shocks on the oil price. It changed, rediverted sort of global shipping. So it was a huge sort of geopolitical event in the closure of the Suez Canal for a decade. And one of the implications of that is that the Panama Canal got a lot busier. And so canals, when they send ships through them, they use locks to raise and lower the ships up and down the canal. And that takes water every time you're using those locks. So by increasing the traffic dramatically, they really increased the amount of water they were using, which lots of the local power was hydroelectric. And the power for the dams themselves and things, they were using hydroelectric power for the canal in various parts. So they had a massive power shortage, and luckily had a spare floating nuclear power plant that they could send. So yeah, it stayed there. I think it did slightly less than 10 years, but it went down there and provided carbon-free power for all that time. The alternative that replaced it was, and still is, fossil fuels. So yeah, I think we were doing some things right back then. So that's sort of a quick trip through the US Army's program. The Navy program is definitely more successful. There's a lot more to point at, but the technology was fairly one-dimensional. So the Navy program was almost solely pressurized water reactors, and they became essentially, if you take all the nuclear power plants that we have on the planet, about 70% of them are pressurized water reactors. That essentially came from that seed of the Navy program. And even, so Rolls-Royce SMR is sort of an example of what we're hoping to build in the UK over on Anglesey, which was the announcement earlier this week, or last week. We're going to be building the first 3 of these on Anglesey in Wales. It's pressurised water reactor, under the hood. It's the same stuff, it's the exact same. So, SMRs of the future. What is an SMR in today's context? So the International Atomic Energy Agency keeps sort of tabs on all of this stuff. They have a dashboard and they publish this every year, small modular reactors, advances in SMR development. It categorises essentially all the various technologies that are out there in the world. They have a minimum threshold to be sort of considered credible and make it into the book. And even with that, there are 60, at the latest count, 68 different technologies across these different groupings. So land-based water-cooled reactors, that's the sort of the boring stuff. And then marine-based cooled reactors, they're the floating stuff that we've just seen, essentially. And then there's a whole host of other sorts of technologies. There's even some that aren't really on here, but again, there's this minimum level of credibility to get considered for as a sort of real technology. But yeah, gas-cooled reactors or high-temperature gas reactors, you might know them as micro-reactors, the sort of deployable, or 5 megawatts of quite small shipping container stuff. Molten salt and liquid metal, and there's different types, so there's different flavours within all of these families. So in liquid metal you could have liquid metal with lead, so it's a lead cooled reactor, or you could have liquid metal with sodium, fast reactor. And various companies at various stages trying to commercialise all of these technologies, including us. So it can be difficult if you don't have a physics degree and a decade in the nuclear industry to sort of sift through the noise to understand what is good, which is the best. There's loads. Which do I pick? And so you have to sort of look at if you look at it as a timeline for what's coming. There's all these 68 plus designs. By the way, if you take those minimum criteria away, if you just look at anyone who's claiming they've got a design, I mean, there's well over 100. I mean, there's probably over 200. There are a lot, and some of them have more money than they should. But if you sift that down to, okay, what's that proven technology that we can commercially, at scale, deploy in a meaningful time frame? And the meaningful time frame for me here is net zero, 2050, right? We've got 25 years, nearly 24. If it's a technology that is interesting, but I need to build a demonstrator, and then I need to validate that demonstrator, and then I'm going to change lots of things, and then I need to operate it for 10 years before I get all the operating experience and the confidence that a load of banks will give me billions of pounds to go and build 20 of them, then it's no use to me. That being said, I sort of split off here AMR demonstrators. So there's a room for still pursuing some of that R&D and building those demonstrators so that in 20 years, if we think we've got something that offers us something better, we can go and do that. So there's only about 14 if you sift it like that. If you then look at the ones that are actually in the major competitions across Europe or the US, you get an even smaller list. And then the ones that are really credible, that make it to the down selects, you've got an even smaller list. So there is only really a handful of those near-term SMR technologies that are going to be deployed at fleet scale and be successful. I would say some of the people on the top track also have insane amounts of technology funding from essentially big tech. They may well build quite a lot of units. I hold a lot of healthy skepticism that they'll be as operationally efficient as they are on paper. So this is the landscape across the world. I mean, we exclude, so in the nuclear industry these days, there's not a lot of mixing between the sort of spheres of China, Russia, who are doing a lot in the nuclear space, with the markets that we would operate in the Western sort of energy markets. And so this is the state of play. So anything with a cross in it is part of a competition that has been down selected, and there's interesting differences between across the Atlantic. So in Europe, the environment's quite good for nuclear. The way nuclear has been handled in the past is usually by state utilities, so people like EDF, who are owned by the French state, people like Vattenfall, who are owned by the Swedish state, people like ČEZ, who are owned by the Czech state. These state utilities that have the balance sheets and the tolerance for risk and the long-term thinking to be able to do nuclear projects, they've got all the capability to operate nuclear power plants. They have all of the ingredients that you need to go and deploy new nuclear of an SMR flavour. And so what we've tried to do, so the Rolls-Royce approach, but largely carries across for lots of these other technologies, is make these things smaller so that they're deliverable. If you can not have. So Hinkley Point C and Sizewell are the big EDF nuclear projects in the UK. So Hinkley Point is under construction currently. Sizewell's just got the go-ahead. Hinkley Point has the world's biggest crane. That's not the nuclear industry's biggest crane. It's the biggest crane in the entire world for anything that someone designed, built, and they use for like a handful of things. Like, that's not an efficient way of doing anything. It's a horrifically inefficient way of doing something. So nuclear had got too big in the past, and it became very hard to deliver. At the same time as nuclear was getting bigger, the West was getting broadly worse at delivering major infrastructure. Environmental regulations were tightening up, health and safety regulations were tightening up. It just became harder to do things. And I don't think we should shy away from that being part of the truth. So by making it smaller, and by taking lots of this stuff into a factory or off-site, you can hopefully speed it up. Nonetheless, you've got to prove that. So of those 5 sort of technologies that you end up at the back end of those funnels, whoever goes first, whoever takes the first punt on one of those, is taking a lot of risk. They're taking a lot of risk that design's good, that the company's going to be able to follow through and deliver on it, that when you build it, it's, there's no major issues, it's delivered on time, on budget, which, probably won't be because it's first of a kind. So that's hard to take that level of risk, and it's the reason that the industry's taken, despite all this enthusiasm, we're only just getting those first projects on the map, and it's because you've got to solve that. You've got to figure out who's taking the risk, which might be every single one of you in the UK. So as the taxpayers or ratepayers, depending on the solutions, you guys are taking the risk, and the government's doing that because in our best interest that we could end up with a load of nuclear power plants that are going to really reduce the cost of our total energy system. So Europe's good, and all these competitions that are now in either ended or in the final stages are starting to create real projects. So we've got one in the UK, we've got one in the Czech Republic, in Temelin, South Bohemia, and Sweden there's 2 technologies left. They down select early next year. They are the big 3. They're the big 3 globally, and they're all 3 projects have state solutions to risk. If we win the 3rd, we have essentially got that pathway to get all of those initial hard units, and then it becomes a little bit like shelling peas. It becomes a bit easier. In the US, there's a lot of noise, there's a lot of capital, but the government doesn't like getting involved. So it's harder to see, even though there's some projects on the map, it's harder to see that they've fully solved this and that they're going to go all the way. And it might be that big tech throws enough money at it that it happens. Bill Gates has backed TerraPower with billions. They've got the funding to go and do their demonstrator, so they don't need to worry about this because Bill Gates is taking the risk. If the sorts of bets these players are willing to take, if you've got a madman with billions of dollars, you can overcome the risk threshold. Interestingly, by the way, I've marked. So France has a national champion nuclear provider, which is EDF. They've sort of deselected themselves in their own competition, and basically said we don't want to deploy our SMR in France. So good luck to them. But there's a few other challenges here as well. So Poland has got a huge challenge. 70% of its energy comes from, or its electricity, not let alone its energy, comes from coal. They rapidly need to get rid of that. And so nuclear's, and they don't have a huge coastline, really. Renewables aren't ideal for lots of their scenarios. Nuclear would be ideal. They've got huge ambitions, but they have zero political stability. And that's a huge challenge, because all that stuff we just talked about, that takes time, it takes long-term thinking, it takes government commitment across parliaments to be able to make a nuclear project happen. It doesn't happen within 4 years. It takes a lot longer. And so in Poland, there just isn't enough stability. They progress, and then there's an election, and then everything's ripped up. So it's very difficult environment. By the way, if there's questions at the end, we can talk about this all day. So as long as there's questions, and I've got a technical background. I did a physics degree, all too long ago. So if there's any sort of, we can delve into the details if we need. Just a little bit, although it's not a sales pitch. This is the Rolls-Royce, so the UK solution in a nutshell. So this is what we're going to get. We're getting 3 of these on Anglesey. We might even get 8 of them on Anglesey. There are a host of other places around the UK that we might be getting them. And that's what it looks like. For context, that sort of structure is like a football stadium. So it's an Old Trafford. Sorry, it's a Britannia Stadium, I should be saying, shouldn't I?
Vale Park.
Right. I'm outdated. And it, so small in the name, but it's still big. These are still big infrastructure projects. And they're not going in a back garden. They're big. They need the right sort of siting. So think, the first places that they're going to go are all old nuclear power plants. So where we're no longer generating, that's the most sensible place for them to go. But it's not the best place if your goal is decarbonisation and net zero. There are plenty more sensible places you could put them. But it's not going in the centre of Manchester. It's not going in the centre of London. So just temper your expectations. It's more like industrial, big industrial clusters like Humberside, like Teesside. And we've got a bit of a unique approach in the UK in that we are the only of all of those technologies, we are taking responsibility for the entire power plant, not just a nuclear reactor bit. And if you look at the cost, all of the clever engineering, yes, all the physics, all that's in the middle, in the reactor. But if you look at the cost of delivering a power station, only about 20% of it is in that reactor bit. So we've decided to take on the scope of the whole power plant, because then we can make it all work. We can handle all the differences, design it all as a get-go, and copy paste from site to site. If you want to know more about Rolls-Royce SMR specifically, then we can talk after. This is essentially what the landscape looks like in the UK. So the blue one, northwest of Wales, so a place called Wilver on Anglesey. That is where the first ones will be going. It's good from a nuclear perspective because there's a lot of space. It's hard bedrock. It's got good access to cooling water, but it's in the middle of absolute nowhere. There's not a lot of interesting things going on nearby that you can provide power to. But unsurprisingly, the island is now of great interest to data centres. It's of interest to people looking to produce future fuels, so sustainable aviation fuels, hydrogen. All these sorts of industries are now taking a great interest in the island because they might have 4 gigawatts of power that they need to get rid of. And so when there used to be a nuclear reactor there, the site had one until early 2000s, I think. There was a whole host of industry on the island. There was aluminium smelting, there was bromine works, there was gas plant works with Shell, lots of chemical processing. None of that exists now. When the nuclear power plant closed down and all the energy disappeared, all the industry died. And so the island is just holiday homes. And they've been crying out for this. The nuclear communities, the dying nuclear communities of the UK are crying out for new nuclear. They all want it. They're all campaigning for it, not against it. In terms of where next, we sort of covered it, but yeah, industrial sites, other nuclear locations. Here's a selection of them, but could be any of those, could be others. It all depends on which developers, which utilities are going to come forward, and ultimately what the government wants to do as well. Just to give you an idea of how close you can put it to things, the picture there is a population density criteria map. And so when you try and get a nuclear site license, you go to the nuclear regulator and you say, here's my design, here's what it looks like, here's my site, my drawings, whatever. And they'll essentially give you a rubber stamp or not. Part of that assessment is the technology safe? But another part of it is, don't put it in the middle of my city. And so there's a rule where you sort of measure around the SMR in a circle, and for every 5-degree segment or something like that, you have to calculate the number of people in every sort of, I don't know the exact detail, like 100-metre block from the SMR. And the closer people are, they count for more. The further away people are, they count for less. And essentially you can't have above a certain threshold. So you can't be really near some people or quite near lots of people. And that shows you, of all of that industrial land around the Humber industrial cluster, there are some places in red where it would be a no-go, but the vast majority of it, you could easily put a nuclear reactor there. If you see this place in real life, it's a genuine industrial wasteland. And the community is happy for jobs. They want jobs to come back or be retained, and so they're not bothered about a nuclear reactor, quite frankly. Which is good, because I think there's a perception that the public are opposed to it, and there will always be people that are. But broadly, the campaign groups opposing these projects, like Hinkley, don't live near Hinkley. They get the train in with their placards. But yeah, so we've covered a lot of this, but the main challenges that are preventing SMRs from really being a critical part of our energy solution and being a big part of the mix are, if you step away from PWRs, all of those other technologies, even within a technology family, they're all going in completely different directions. They need completely different developments, different materials, different fuels, and there's no synergy in the R&D. And so you've got to, if you don't know which horse is going to win, how do you consolidate? If you're a government, how do you consolidate your investment in supply chain and things like that? Because you just don't know. Do I need that way? And so because they're all pulling in different directions, no one's getting anywhere. And that's not quite true. Things are moving forward in all those directions. But if they were all closer aligned and we were to say, here's the technology we want, that's good direction from governments, and it can enable people to coalesce around a single technology and drive it forward. Even if you do that, though, nuclear development is hard and it's very expensive. The very boring stuff of Rolls-Royce SMR will be well over £1 billion of development cost just to do the technology. That's before we even put a spade in the ground. Just to do the design and get it licensed will be well over £1 billion. And someone has to pay that. So Rolls-Royce has paid some of it. Some of the other shareholders have put money in. The UK government's put some money in. But there's a huge amount of capital that you are not going to get any return on. We don't become profitable for the next 5 years. So for the next 5 years, we continue to burn more money than we make. It's a terrible business model. It's a terrible business model. Why would anyone do it? Then the licensing processes can be onerous. Every country has its own. So if we were going to build these in the UK, we're nearly through the UK regulatory process. But we now want to go build these in the Czech Republic as well. Well, we have to start again, essentially. Now, we're doing our best, and the industry is doing its best to try and bring some of that together and harmonise regulations, but it's difficult. What's at stake here, back to the Rickover principles. No one wants to be the one that says, the UK said it was all right, it's probably fine. They built it. So you have to start again in every country. The US has a bit of an edge there because although all the states are different and competing, there's only one regulatory process for the whole country. So, but even so, even if all those US technologies want to come and deploy in Europe, they face the same challenge. And the supply chain has faced 2 decades of atrophy. So there's been huge disinvestment in the nuclear industry for so go back sort of 30 years ago, there was 2 decades of disinvestment. We've now had about a decade of investment through largely the submarines program in the UK, but also the resurgence of these SMR and other nuclear projects. So the supply chain is about at its minimum, to be honest. It's really just starting to turn that corner, and there's a huge hill to climb. If we're going to be building loads and loads of these every year, and all the other technologies are going to be building loads and loads, the supply chain's not ready because it's faded away. There's been no cause to invest in facilities, so facilities are getting older, people are getting older. So we're starting to sort of turn that around, but it's not easy. And again, the different technologies have different component needs and different suppliers, so they can't even standardise across that. And then the trivial matter of finding a few £1 billion per SMR is also a difficult one. You need to make this work a pipeline of orders. So if we get the 3 orders from the UK government, great, that's 3. But that's 3. What's next? I need 50 because I need to tell the guy making my pumps that I want 50 of them. I don't want 3, because if I want 3, they're very expensive. If I want 50, they're moderately expensive. So we need to get that pipeline of orders and finance flowing such that we as OEMs can make the commitment into the supply chain and do those bulk buys, and that's more risk. People are taking risk by doing that. Those projects are going to go ahead and they're going to get their money back. So there's risk everywhere you look with nuclear, which is why it needs government support, especially in the early days, to deploy it. And then if you don't have that clear government policy, a la Poland, it's then very difficult, almost impossible. And I think the UK is okay, but in terms of energy policies at the highest level, there is no good integrated energy policy around how the hell we achieve net zero. And some of the stuff around clean power 2030 just, is not achievable. So there's lots of challenges, but I think we're getting there, and it's been a good news week. We are off the starting line in the Czech Republic, in the UK. I'm confident that this will be a good thing for the country, it'll be a good thing for the world, for export markets, and just for decarbonisation in general. We do lots of work with sort of end users of energy, whether that's hydrogen producers, steelworks, data centres. All of the hyperscalers have been all over us like a rash for the last 18 months. They genuinely cannot get enough energy. They'd have bought 50 of these if we could deliver them tomorrow. But unfortunately, the first one is in the sort of mid-2030s time frame, which is the quickest we can do it from where we are today. But it's all too late, really, given we're sort of 9 years closer to 2050 by that point. I'll open up to questions, I guess. Yeah.
I think so. Sorry, but first and foremost, thank you very much.
Yeah.